Namaskara. Dear students, this is the second video class for my second BSc students on wave motion. In the second class, I want to deal with the differential equation of a progressive wave on a string. In the examination, the question may be like this. Obtain the differential wave equation on a progressive wave of a progressive wave on a string. See, to obtain the differential equation of a progressive wave on a string. Before going to actual derivation, we want to know what do you mean by progressive wave. In the last class, we have defined progressive wave. Progressive wave is a wave which propagates continuously in a medium in the same direction without any change in its amplitude, frequency and wavelength. To obtain the differential equation of a progressive wave on a string, let us consider a stretched string PQB, one such stretched string. In the stretched string, there may be a crest and trough. Let us consider one such crest P, A dash, B dash, Q, B, one stretched string. Let us consider A dash, B dash, the displaced position of the element at any instant of time t second. This displaced element A dash B dash is being acted by a force called tension. This is the one tension acting at B dash. This is the another tension T acting at A dash. These two forces acting in opposite directions. Let us consider the points A dash B dash are subjected by two different tensions. One is this one, the other one is this one. Let us consider the tension T at B dash can be resolved into two components. One is horizontal component, the other one is vertical component. This tension T can be resolved into two components. One is horizontal component along this direction, vertical component along this direction. I mean, these two forces are acted by both horizontal and vertical components. Let theta plus delta theta be the angle subtended by the tension T at B dash with the horizontal component. Let us consider the angle theta. The angle theta is subjected by the tension T with the horizontal component along this direction at A dash. At A dash, the horizontal component can be written as T cos theta. Vertical component at A dash can be written as T sin theta. Similarly, the vertical component and the horizontal component at B dash can be written as horizontal component at B dash B, T cos theta plus delta theta, and vertical component at B dash B, T sin theta plus delta theta. Here, the 2 points A dash B dash are acted by horizontal components are acting in opposite directions, vertical components are acting in opposite directions. Therefore, the net horizontal component net horizontal component, net horizontal force or horizontal components is given by t cos theta minus t cos theta, that is t cos theta plus delta theta and t cos theta. As we know that if theta is very small, sin theta is almost equal to theta, tan theta is almost equal to theta, cos theta is almost equal to 1. Therefore, if theta is very small, cos theta is almost equal to 1, cos theta plus delta theta is almost equal to 1. Hence, t cos theta plus delta theta is reduced to t cos theta is reduced to t minus t is 0. Therefore, net force acting in horizontal components, net forces acting in horizontal components is 0. Net force acting in horizontal components is 0. Similarly, net forces acting in vertical components is given by t sin theta plus delta theta minus t sin theta. As I told you, if theta is very small, sin theta is almost equal to theta, sin theta plus delta theta is almost equal to theta plus delta theta. This is reduced to, t sin theta plus delta theta is reduced to t into theta plus delta theta minus t sin theta is reduced to t theta. If I simplify t delta theta, we can write. That is, as I told you, theta is very small. If theta is very small, tan theta is almost equal to theta. Hence, instead of writing theta, I want to write tan theta. That is, net horizontal component is t delta tan theta. If I consider the tangential line, this is the tangential line. As I told you, this is known as x-axis, this is known as y-axis. If I consider the slope here, slope here, delta y by delta x. This tan theta clearly explains the slope, that is delta y by delta x. Instead of writing tan theta, I want to write delta y by delta x. Therefore, net force acting in vertical component is T into delta y by delta x. That is, the net force in y direction is T into delta y by delta x. Delta y by delta x. T into delta can be written as multiply and divide by delta x. Delta by delta x. Delta y by delta x. Clear? Next, T into del square y divided by delta x squared into delta x. Right. From Newton's second law, the mathematical equation for Newton's second law, force is given by mass into acceleration. That is, the product of mass with acceleration is equal to the net force acting on the element. M into delta x. What is M into delta x? M into delta x explains mass of the element with the length delta x. Mass of the element with the length delta x. That is, M into delta x is nothing but mass. Del square y by delta t squared explains? Del square y by delta t squared explains acceleration. Mass into acceleration. Instead of writing force, we want to write mass into acceleration. That is equal to T into del square y by delta x squared delta x. That is del square y by delta t squared is equal to t divided by m del square y by delta x squared. This delta x and this delta x goes off. Here m mass of the element per unit length of the string. M into delta x, mass of the element of the length delta x. Del square y by delta t squared is acceleration. I mean del square y by delta t squared is equal to t by m into del square y by delta x squared. This clearly explains the differential equation of a progressive wave on a string. This clearly explains the differential equation of a progressive wave on a string. Thank you one and all.